Mathematical induction. Let's say we want to add all the numbers up, or sum them up, all the way up to n, for any particular n. We have a formula for that. It's n times n+1 over 2. This works for all positive integers. First step is we prove it's true for n equals 1. That's our base case. Second step is we assume it's true for n equals k. K is also a positive integer. Part of that step is we then have to prove that it's true for k plus 1. That's our inductive step. That's the tricky bit. The last step is we simply state by mathematical induction it's true for all n. Okay, let's prove that it's true for n equals 1. Well, we won't need all of these numbers, we just have 1. The sum of all the numbers up to 1 is just 1. So let's try the formula. Swap these n's for 1's. So that's 1 times 1 plus 1, all over 2. That comes to 2 over 2, which equals 1. That's correct. We could try this for other numbers, but for now all we need is just that first case, the base case. So it's true. Second step, assume it's true for k, as in n equals k. Well, we've just done that. Simple as that. Now part of that, we have to now prove, and this is a tricky bit, for n equals k plus 1. So we sum up to k plus 1 using our assumption. So there it is, 1 plus 2 plus 3 all the way to k, and we're going to use our assumption for that, plus k plus 1. We keep those two separate and we include the k in there. So now let's use our formula for up to k. K times k plus 1. Now what does this all equal? Well, we need to get the same common denominator, so we make that 2. And we also can just put that all over 2 now, and we'll notice that we have a common factor of k plus 1. So we can take that out the front. So we'll have k plus 1 times k plus 2. There. That's the answer for summing all the numbers up to k plus 1, assuming it's true for k. Now use the formula for k plus 1. Remember on the left hand side we used it up to k, but we didn't use it up to k plus 1. So on the right hand side, let's see if it equals using the formula for k plus 1. Well, there's our formula, n times n plus 1. Let's just move those apart a little bit. And let's just substitute in k plus 1. There, now do those two results look the same, the left hand side and the right hand side? They do. It's true. So we've just proved that's true for k plus 1, assuming it's true for k. Now we simply state by mathematical induction it's true for all n. So a good question is, how can we assume it's true for k, then use that to prove it's true for k plus 1? Isn't that somehow a circular reference? Well, we can, because we proved it's true for n equals 1. I'll show you. We simply let k, in our assumption that it's true for k, equal to 1, which we know is true because we proved it. Therefore k is true in this particular case if k equals 1. Well, if k is true, we proved that it's true for k plus 1. That means it must be true when you sum up to 2. Now instead of using k equals 1, we could now say, well, we've just proven that it's true for 2, so we could let k equal 2. And whenever k is true, we know k plus 1 is true. So if it's true for 2, it must be true for 3. We could do this forever, all the way to infinity. So it's true for all n. That's it. We have proven that 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2 by mathematical induction.